Lesson 1.6 focuses on complements and odds. We've looked at complements for sets, and now we're going to consider how complements apply to probabilities. In any experiment, an event must either occur or not occur. Consider rolling a die. You're either going to roll a 5 or not roll a 5. So let's look at the probability for each of these. The probability of rolling a 5 is 1/6. There's one way to roll a 5 out of 6 possible outcomes. Well, the probability of not rolling a 5 is 5 out of 6. There's 5 numbers that are not 5 out of the 6 possible outcomes. Well, what do you notice about these two probabilities? If I add them, I'm going to get a 1. The two events mentioned are considered complements. Two events are complements if these following two things occur. First, together they make up the entire sample space. If I considered my sample space for rolling a die, I had the numbers 1 through 6. Rolling a 5 took care of the 5, and not rolling a 5 took care of the 1, 2, 3, 4, and 6. So every number in my sample space fit into one of those two categories, either rolling a 5 or not rolling a 5. The second condition of complements is the two events cannot possibly occur at the same time. If I roll a die one time, I cannot roll a 5 and not roll a 5 at the same time. Let's look at another example. If I toss a coin, let's say my first event is tossing a head and my second event is tossing a tail. I want to know if these are complements. Well, together, do they make up the entire sample space? And they do. Tossing a coin, my only two options are tossing heads or tails. Second, can they occur at the same time? And they cannot. I cannot toss a coin one time and it land on heads and tails. So since the two events make up the entire sample space and they cannot occur at the same time, they are complements. Well, let's say I roll a die. Event A is rolling an even number and event B is rolling an odd number. So the first condition, together, do they make up the entire sample space? And they do. When I roll a die, every number in my sample space is either even or odd. And second, can the events occur at the same time? And that's no. If I roll a die, it is not going to roll an even number and an odd number at the same time. So both of my conditions of complements are met. So these events are complements. Now let's look at some examples that are not complements. Let's say I roll a die and I roll a number greater than 3 and roll an odd number. Well, rolling a number greater than 3 means rolling a 4, a 5, or a 6. Rolling an odd number means rolling a 1, 3, or a 5. This example fails both conditions of my complements. First, I can notice when I list them that 5 is listed in each event. So it is possible to roll one die and it satisfy each event. That number is greater than 3 and it's an odd. So these are not complements. With complements, your two events cannot share any possible outcomes. It also fails the first condition of a complement because it doesn't account for the 2. If I roll a 2, that number is not greater than 3 and it's not an odd number, so it doesn't fit into either event. The complements have to cover the entire sample space and they cannot have common outcomes. Let's look at another example. Say I roll a die and I want to know if event A is rolling a number greater than 3 and event B is rolling a number less than 3. Well, event A is rolling a 4, a 5, or a 6. Those are greater than 3. Event B is rolling a 1 or a 2. If you notice, the option of rolling a 3 is not present in either event. So these are not complements because 3 is not in either event. Well, there's several ways to denote a complement. And as we looked with sets, if our event is E, the complement of E is going to be E with a bar over it. For example, if the probability of drawing a red marble is P of R, then the probability of not drawing a red marble is P of R complement, where the R has the bar over it. Well, we saw in a previous example that the sum of the probability of an event and the probability of the complement of that event was 1. So that gives us a formula we can work with. If we're given the probability for an event and we needed to know the probability of that event's complement or vice versa, we could just subtract from 1. So the probability of the complement equals 1 minus the probability of an event. And likewise, the probability of an event equals 1 minus the probability of the complement of that event. Well, from time to time, you're going to be asked for the probability of an event not happening. And sometimes it's easier to find the probability that the event will happen, which is its complement, and then subtract that result from 1. So let's look at an example. A couple plans to have 3 kids. What is the probability of not having exactly 2 boys? Not having exactly 2 boys includes several options. That means I could have 3 boys, I could have 1 boy, or I could have no boys. Let's consider the complement of this. The complement to not having 2 boys is having exactly 2 boys. If I find the probability of this complement, I can use it to find the probability I was asked for. So the probability of not having 2 boys is 1 minus the probability of having 2 boys. It's easier to list the ways to have 2 boys. Remember, I could have boy, boy, girl, boy, girl, boy, or girl, boy, boy. So there were 3 ways that this happened. If you remember, the number of elements in my sample space for having 3 kids was 8. We got that because for each child there were 2 outcomes, and 2 times 2 times 2 gave me 8. So the probability of having 2 boys was 3 out of 8. If I subtract that from 1, then I get that the probability of not having 2 boys is 5/8. Let's look at another example. I roll a fair die. Find the probability of rolling a 2 or higher. Now this one is fairly easy. We could do it straightforward. If I draw a 2 or higher, there's 5 ways to do that. So I know my probability is going to be 5 out of 6. But let's look at this example using complements. The complement of rolling a 2 or higher would just be rolling a 1. So the probability of rolling greater than or equal to a 2 is 1 minus the probability of rolling a 1. Well, the probability of rolling a 1 is 1/6, and the 1 minus 1/6 gives me the 5/6 that we mentioned before. And when you're working these problems, you can either work them straightforward and get the 5/6 as we did at the beginning, or you can work these using the complements. Just use whichever method is easier for you. So let's look at a few examples. Consider drawing a single card from a deck of cards, and I want to find the following probabilities. First, let's look at the probability for drawing a red card. Well, there's 26 red cards in a deck, and there's 52 total cards. So the probability of drawing a red card is 26 out of 52. And that reduces to 1/2. Basically, half of the deck of cards is red, so your chances of drawing a red card is 1/2. Next, the probability of drawing a spade. Well, a spade is one of your 4 suits, and there's 13 cards in each suit. So the probability of drawing a spade is 13 out of 52. And that will reduce to 1/4. Now let's look at the probability of drawing a 7. There's 4 sevens. There's a 7 for each suit, and there's 52 total cards. So the probability of drawing a 7 is 4 out of 52, and this reduces to 1 out of 13. So the probability of rolling a 7 is 1 out of 13. Well, now let's look at the probability of not drawing a 7. Since I just found the probability of drawing a 7, it's going to be easier to use complements. The probability of not drawing a 7 is 1 minus the probability of drawing a 7. So that's 1 minus 1/13, which is 12/13. And don't forget, you can use your calculator for the fractions to make this easy on you. Well, the next example is find the probability of drawing a face card. The face cards were the Jack, King, and Queen in each deck, so there were 12 face cards. So the probability of drawing a face card is 12 out of 52. This reduces to 3 out of 13. Well, the next example is find the probability of not drawing a face card. Again, I'm going to use the complements. So the probability of not drawing a face card is 1 minus the probability of drawing a face card. So that's 1 minus 3 out of 13, and that gives me 10 out of 13. Unless told otherwise, always give your answers as reduced fractions. Next, let's look at odds and probability. Sometimes probability statements are expressed in terms of odds. If you are given the probability of an event, you can find the odds for that event. And we generally discuss odds in terms of favorable odds, the odds for an event. And sometimes we are asked for the odds against an event. Odds are basically another way of expressing the likelihood of an event. When comparing probabilities and odds, pay attention to the wording. So let's look at determining the odds when you're given the probability. The odds for an event are found by finding the probability for the event and dividing it by the probability against the event. The odds against an event can be found by dividing the probability against the event by the probability for the event. So notice how the words match up. Whichever odds you're asked for, that probability goes on the top of the fraction, and its complement goes on the bottom. If we're asked for the odds for the event, we put the probability for the event on the top of the fraction. If we're asked for the odds against the event, we put the probability against the event on the top of the fraction. As I mentioned before, the probability against an event is just the complement of that event. Now, unless told otherwise, you always write probability as a reduced fraction. I want a way to distinguish between the odds and the probability. So when we're given the odds, I want you to write it as either A to B or A colon B. Don't ever write odds as a fraction. Always write odds in the ratio forms using the word to or using the colon. So let's look at an example. The probability that a horse will win a race is 1/5. Find the odds for the horse. I'm asked for the odds for, so let's find the probability for a win, and that's what we were given, which was 1/5. The complement would be the probability of a loss, and 1 minus 1/5 is 4/5. So for the odds, I'm going to put the probability of a win divided by the probability of a loss. So I'm going to have 1/5 divided by 4/5. When I divide these, I get 1/4. So I'm going to say the odds for the horse are 1 to 4. Don't leave it the fraction 1/4. Write it in the ratio form using the word to or using the colon. Well, in the next example, the probability that a horse will win a race is 1/5. Find the odds against the horse. This time, since I'm asked for the odds against, I want to put the probability of a loss, or the probability against a horse, on the top of the fraction. So the odds against are the probability of a loss divided by the probability of a win. So that's 4/5 divided by 1/5, which is just a 4, but remember in fraction form it would be over and understood 1. And I needed the fraction form to get the ratio, so the odds against the horse are 4 to 1. And if you notice, since the example didn't change, the probability for the horse winning didn't change, the odds for the horse and the odds against the horse are just reverse of each other. Let's look at the next example. The probability of rain is 1/3. Find the probability that it will not rain. So we're told the probability of rain is 1/3. The complement of that is 2/3. So the probability that it will not rain is 2/3. I got that by saying 1 minus 1/3. Now look at what you were asked for the odds for. You were finding the odds that it will not rain. So I'm going to put the probability that it will not rain over the probability that it will rain. So I have 2/3 divided by 1/3. If I divide these, I get a 2, but I'm going to leave that 2 over 1. So the odds that it will not rain are 2 to 1. Next, we want to look at determining the probability when we're given the odds. So suppose you are given the odds for an event and you want to find the probability for that event. If the odds for the event are m to n, then the probability for the event is m over the sum m plus n. The reverse of that, or on the other hand, if the odds against the event are m to n, then the probability for the event is n over the sum m plus n. You've got to pay attention to the words. If the words match, if I'm given the odds for and I'm finding the probability for, or if I'm given the odds against and I'm finding the probability against, if those words match, I put the first number from the odds over the sum of the two numbers. If the words do not match, so if I'm given the odds for but I'm asked for the probability against, or if I'm given the odds against and I'm asked for the probability for, I use the second number from the odds over the sum of the two numbers. So let's look at some examples. If the odds in favor of a victory are 7 to 3, find the probability of a victory. This time my words match. I'm given the odds for a victory and I'm asked for the probability for a victory. So I'm going to use the first number over the sum. So the probability of a victory is 7 over 7 plus 3, which gives me 7/10. If the odds in favor of a victory are 7 to 3, find the probability of a loss. This time my words don't match. I'm given the odds of a victory, but I'm asked for the probability of a loss. So this time I'm going to use the second number over the sum. So the probability of a loss is 3 over 7 plus 3, or 3/10. So if the odds for rain are 2 to 1, find the probability that it will rain. This time my words match, so I'm going to use the first number over the sum. So the probability of rain is 2 over the 2 plus 1, which is 3. And then the final example, if the odds for rain are 2 to 1, find the probability that it will not rain. This time my words do not match, so I'm going to use the second number over the sum. So the probability that it will not rain is 1 over 2 plus 1, or 1 over 3.